In the previous video, we looked at how to generate the coefficients of each term in an expansion using Pascal's triangle. Now, in this video, what I want us to focus on is on the powers of a and b in the expansion of a plus b to the power of n. And in this specific case, we will be looking at the expansion of a plus b to the power of 4. Now, the first thing that we have to do here is basically to look back at what we did and then try to look at some patterns that will help us to generalize some observations. So previously what we looked at was that we found out that a plus b to the power of 4, so a plus b to the power of 4 is given by this expression. So we did expand it, okay, and using this method to end up with this expression that's equal to a plus b to the power of 4. But we now want to look at each term and look at the powers of a and b and see if we can come up with something. So I'm just going to copy this here. So a plus b to the power of 4, so a plus b to the power of 4 is equal to a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. So if you look at the patterns, if you look at the powers of a, we can notice that a starts at a to the power of 4, okay, and then basically if I use a hat, so you have a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, and a to the power of 0. So I'm just going to add those ones. So a to the power of 1 and a to the power of 0. Of course, a to the power of 0 is 1, and that's why it's omitted here. So we can say in our key observations or important observations, we can say that the powers of a start at 4 and go down this way. So we have 4, 3, 2, 1, and 0. And that's what's happening here. Let's look at the powers of b. Now, for the powers of b, we have powers of b going up. So we have here something like b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3, and b to the power of 4. So if I use a highlighter, so you have b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3, and b to the power of 4. So we can generalize and say that the powers of b go upwards, and they go upwards in this pattern. So powers of b go upwards, starting from 0 to 1 to 2 to 3 up to 4. Now, another thing that we can notice is that in each term the powers add to 4. Okay, so if you notice, in each term the powers add to 4. Like in the first term, 4 plus 0 is 4, 3 plus 1 in the second term, that will be 4, 2 plus 2 will be 4, and so on. So we can say that the powers in each term add up to 4, whereby 4 is what actually the power of the binomial is, what n is. Okay, of course, we had a plus b to the power 4. And we can notice that in each term, the powers add to that. They add to 4. Okay, um, let's now look at how we can apply this in expanding this. Remember, we've looked at how to use Pascal's triangle to generate the coefficients, and we also looked at how the powers of x, a, and b um, change in each term. So using those patterns and ideas, we can be able to expand a question like this one here. And let's see how we can apply that idea here. So, expand at x plus y to the power of 5. The first step is to generate the coefficients. Okay, this is, now the coefficient that we need here is when n is equals to 5. And I'll just put up a Pascal's triangle. Okay, so when n is equals to 5, this will be the coefficients. Okay, because this is when n is equals to 0, n is equals to 1, n is equals to 2, n is equals to 3, n is equals to 4, and n is equals to 5. So these are the coefficients that we need, which are 1, 5, 10, 10, 5, 1. And you can be able to, you can actually produce this triangle without using a calculator. Okay, so our coefficients are 1, 5, 10, 10, 5, 1. So our step 1 is to find the coefficients, and we have them. So our coefficients are 1, 5, 10, 10, 5, 1. That's my first step. The second step is to fill in the powers of the first term. Okay? Now, the powers of the first term will be the powers of x. And they start from x to power 5 all the way up to x to power 0. So we'll have x to power 5, x to power 4, x to power 3, x to power 2, x to power 1, and x to power 0. The next step is to fill in the powers of the second term. Okay? And the second term is y. And these ones here are increasing from 0 to 5. So y to the power of 0, y to the power of 1, y to the power of 2, y to the power of 3, y to the power of 4, and y to the power of 5. And then what we want is just to simplify this. So let's go ahead and simplify each of these guys. Okay? This will be x to the power of 5. Just use laws of indices. This will be 5x to the power of 4y. This will be 10x cubed y squared. And this will be 10x squared y cubed. And this will be 5xy to the power of 4. And this will be y to the power of 5. Now, what you're going to do next is to add all this. Okay? So we add these terms to get our expression for the expansion of x plus y to the power of 5. So, and that will be what you're looking for. So we can go ahead and say that x plus y to the power of 5 will be what we had first, which is x to the power of 5. What we had second, which is 5x to the power of 4y. And then what we have third is 10x cubed y squared. And then 10x squared y cubed. And then 5xy to the power of 4. And then y to the power of 5. And that is our solution. Next example, expand 2k minus 3 to the power of 6. And we'll use the same method. So the first step is to find the coefficients from Pascal's triangle. Now here's our Pascal's triangle. And in this question, we can see that n is equals to 6. So we have to go here and inspect. This is the row that represents n is equals to 6. This one here. So basically, these are the coefficients that we're looking for. And what you need to do now is just to write the coefficients here. So we have 1, 6, 15, and I'm just writing those coefficients from here. Okay, 15, 20, 15, 6, and 1. So that's the first step. The second step is to fill in the powers of the first term. Okay, the first term is 2k. Now remember, the powers of the first term are starting at 6 and descending. So what we'll have here is 2k to the power of 6, 2k to the power of 5, 2k to the power of 4, 2k to the power of 3, 2k to the power of 2, 2k to the power of, that's 2, 1, and 2k to the power of 0. The next step is filling the powers of the second term, and the second term is negative 3. Okay, not positive 3, it's negative 3. Okay, and the powers of negative 3 start from 0, ascending. So negative 3 to the power of 0, negative 3 to the power of 1, negative 3 to the power of 2, negative 3 to the power of 3, negative 3 to the power of 4, negative 3 to the power of 5, and negative 3 to the power of 6. And then the next step is to simplify each of these. You may need to use your calculator because the numbers here are big numbers. So the first one you can just simplify. That will be 64k to power 6. The next one will be negative 576k to power 5. The next one will be 2160k to the power of 4. And this one will be negative 4320k to the power of 3. The next one will be 4860k squared. The next one will be negative 2916k, and the last one will be 729. And then what you need to do now is to add all these terms. Okay, so we need to add these terms. And when we add them, that's what will give us the expansion of 2k minus 3 to the power of 6. So basically, 2k minus 3 to the power of 6 will be equal to whatever we had for the first term, which is 64k to the power of 6, minus 576k to the power of 5, plus 2160k to the power of 4, minus 4320k to the power of 3, plus 48 60k squared, minus, so that will be minus 2916k plus 729.